We're going to solve LeetCode 166, fraction to recurring decimal. I've solved this problem before, but it was quite some time ago. So we're going to reattempt this today. And I remember that you have to know long division to be able to solve it. So I pulled up an example of how to do long division, which we will have a look at in a second here. But first, let's try to understand what this problem is about and what we actually have to do. So we're given two integers representing the numerator and denominator of a fraction. And we need to return the fraction in a string format. If the fractional part is repeating, we need to enclose it in brackets. If multiple answers are possible, return any of them. Okay. And it's guaranteed that the length of the answer string is less than 10 to the 4. Okay. All right. Let's have a quick look at the constraints before we look at the example. So we can see that the numerator and denominator are 32-bit signed integers, and the denominator cannot be 0. So we will never have to deal with the case where we have a division by 0, which is nice. But we might have to deal with negative numbers as well. Okay. Well, we do have to deal with them, right? Okay, so let's look at the examples. First example, numerator is 1, denominator is 2. So the fraction is 1 over 2. The result is 0.5. Okay. Second example, we have a numerator of 2 and denominator of 1. We have no fractional part. The result is just 2. And example 3, we actually have a repeating fractional part. We divide 4 by 333. And then we get 0 point followed by a repeating fraction. Okay. So what these examples tell me is that the numerator can be smaller or larger than the denominator. We can have repeating fractions. We can also have no fractional parts. And we can also have no non-fractional parts. So nothing before the decimal separator. Okay, so yes, so in order to do this, you have to know how long division works. I'm just thinking, I think, yes. So I think we can deal with the, well, I think we should take care of the sign first, right? Because if we do a long division, why should we want to keep worrying about the signage of stuff? So I think we need to make sure the numerator and denominator is positive when we go into the long division, but we need to know when we have to add a minus sign to our result string. So let's deal with that first. So when is the fraction going to be negative? Well, it's going to be negative if only one of the two, numerator and denominator, is negative, right? If any of, well, and if the numerator is 0, that means the result is 0. But if the denominator is negative, we don't want to return minus 0. So the first thing we do, I think that's an edge case, we should take care of it. So if the numerator is equal to 0, we're just going to return 0. Return 0. Now we have to check if the numerator is smaller 0 and the denominator, we know it can't be 0, so it will either be smaller or larger 0. In that case, we have to add the minus sign. And the other case is where we have exactly the opposite, right? Where the numerator is larger 0 and the denominator is smaller 0. Then we also have to add a minus sign. We can combine these two with an exclusive OR. And in Python, you do that with the caret symbol. Where is it? Where is my caret? There it is. Okay, cool. And so if the numerator is smaller x or the denominator is smaller than 0. In that case, we have to add the minus sign. Now, since we're going to build our result string incrementally, digit by digit, I would suggest we use an array to store those digits. Otherwise, if we have a string and we add a character to it, we create a new string. right, which is then O of n. If you do that n times, it's O of n squared. So we don't want that. So what we do is we create a result list. And at the very end, we're going to just join all of the strings and digits that are in our result list together. And for the minus sign, we just append the minus sign to our result in this case. Right. So the next part, I think, if we have the case where the numerator is larger than the denominator, I think we should just calculate the part that comes before the decimal point. That's going to be easy. That's a one-time thing. So let's deal with that. So the way I like to do that is I calculate the integer division of the numerator by the denominator. So that would be 2 in this case. And then I compute the rest, the remainder, that we still have to divide by the denominator. And so let's take care of that first step. The integer division of the numerator divided by the denominator looks like this. In Python, you just do this. This is integer division. And now we need to also compute what the rest is. And most people should know this. You just use the modulus operator. If you don't know how integer division and modulo operator work, just look it up. You have to know that. And it's not that complicated. So yeah, cool. So now, if the rest is now 0, like in our example 2, we're done. We don't have to add a decimal point, right? We're done. That's it. But if it's not 0, we know we need to append a decimal point. And we're only going to do this once, so this is why we can do this here. Now we actually need to go into the long division part. And we're going to use a while loop for that. And let me just show you how long division works. This is more like a refresher. I'm probably not able to explain it very well, but the way it works is, so we've taken care of the part where the numerator is larger than the denominator. And what we're left with now is just the rest that we need to divide again by the denominator. And for simplicity purposes, I'm just going to say, okay, the numerator is now the new numerator is now the rest, right? So, and as long as that's the case, we're going to be in our little while loop. So we have the case where the numerator is smaller than the denominator. That's how we start to go into the while loop. And the numerator is not 0, right? Which means we have to do the long division. And the way it works is we now try to divide 8. So in this example, we try to divide 8 by 11. That of course doesn't work because we know the numerator is smaller than the denominator. So the first thing we need to do is we need to shift the numerator 1 digit to the left. And in decimal representation, the way to do that is by multiplying with 10. So I'm just going to do that real quick. By 10. And now we're dividing 80 by 11, right? 80 by 11. So it's just 80, and we're going to divide it by 11. That works. If we do an integer division, we know that 77 is the largest multiple of 11 below 80. So it knows the integer part of the division is 7, which yields us our next digit in our result that we have to append. And the remainder, or the rest, will be 3. So that will be 80 modulus 77, and that's going to be 3 because that's the difference from 77 to 80. So now again we have we have the next digit, which is the integer division, and we have a new rest, which becomes our new denominator for the next iteration of the loop. In the next iteration of the loop, we have 3 divided by 11. 3 is too small, so we multiply it by 10, which we do in every loop step. So now we have 30 divided by 11. We know 22 is the largest multiple of 11 below 30. And so the next integer division digit gives us our next digit 2. And then we calculate the rest, which is 8. And now something happens that tells where we see a previous rest or remainder occurs that we've seen before in our long division. That tells us that we found a repeating fractional part. So the digits 2 and 7, they will now repeat indefinitely. Right, so yeah, we just need to translate that into code and do the while loop. And all we really have to do is we have to calculate the integer division again and the rest. I'm just going to write this into a single line, just so it's a little easier on the eyes. So we just calculate that part, the integer division. And we're going to append to our result the string of the integer division. And by the way, we forgot to do this here. So we have to do this here as well in the very beginning, right? And if the integer division is 0, then we will append the 0 here before we add the dot. So this is this case. So all of that should be good. So yeah, so we do exactly the same thing that we did up here, down here. And now we just have to, well, set our numerator to the rest. So, and that will now compute the complete long division. However, it will not abort when we find a repeating pattern yet. So we need to have a way to identify if we've seen the rest before, or if it's basically a new one. So the way we can do that is we can simply check before we start to calculate step. We will just check if the numerator has been seen before, right? So and for that we need a little helper, I guess. Well, we probably need, well, we need to remember where we've seen it and that we've seen it. The where we've seen it is important to identify where the repeating fraction starts, and that we've seen it helps us to identify that we are seeing a repeating fraction. So I'm just going to use a Python dictionary here, and what we do is if numerator in seen, that means we've seen the 8 before. If we've seen the 8 before, then we know, well, one thing we know is that after dealing with this, we're done. We're not going to continue to calculate the long division. So we will get the position of where we've seen this numerator first. Right, so we just get that. And now we're going to add the parentheses to our result. And yeah, and we can just do this with list concatenation. So we're going to use the list up to the position where we've seen it. Plus we're going to add the opening bracket. Okay, there we go. And we're going to add the rest of the result list that we computed so far. That contains the repeating fractional part. And that is from the current position until the end of the result. And then we just add the closing brackets. And that's pretty much it. I think that should be everything. Oh, well, if we've not seen the numerator, we need to make sure that we add it to our scene dictionary, right? And we're going to put the length of the result. So I think that should be it. I think yes, I think that should be it. Now in terms of runtime complexity, excuse me, in terms of runtime complexity, the question really is, excuse me, how long do we have to go down this I guess I would call it step away, doing the long division. And now this can be actually very long. I have no good way of deriving this myself, but I remember that it's dependent on the length of the denominator, right? So it's actually O of denominator time, if I'm not mistaken. O of length denominator time, and well, space as well, right? Because if we go down n steps, that means we're going to have a result that has length of n. So I think that is fair to say. And we could also say, no, I think that's it. That's pretty much it. Well, there's also a part where, well, the first step, right? It's not free, but in this runtime analysis, I assume that every division, every modulus, every addition or subtraction is O of 1. You could assume that because you only need 32 bits to represent the numbers, but you could also misuse that fact to say everything is O of 1 because the length of the numerator and denominator is limited. So I guess, to be completely correct, you probably also have to use the log of the denominator, because typically operations on numbers with n digits is a log n operation. Even though on a CPU, some of these operations are O of 1 time, depending on how large these numbers are. But yeah, I guess that's more an academic discussion. After this, I'll probably look up what other people say what the runtime is. But yeah, I'm not too sure about that. Actually, let's look that up in a second. So now we just want to see whether what we've built actually works. So I will just run through this one more time with the mental debugger. Okay, so we've taken care of the edge case where the numerator is 0 and where the denominator is smaller than 0. We don't want to return -1, so we just return -0. We want to return 0 directly. Result. So this is where we build up our resulting string. We take care of the sign. If exactly one of the numerator and denominator is smaller than 0, that means we have to add the minus sign. Then we do the first integer division to compute the part that comes before the decimal point. Then we add the decimal point if we know that we need to continue. And just going to swap those lines around. So those 3 lines are exactly the same 3 as down here. And yes, so we have to do a one-time check. Are we going to go into while loop or not? If we are, we're going to append a decimal dot. Next, we're going to use a hash map to keep track of the remainders that we've seen so far to identify the repeating pattern. If the numerator has been seen before, that means we've found a repeating pattern, and we can just add our parentheses around that repeating pattern part. Right? The repeating pattern doesn't have to start right after the dot. It could occur, somewhat later in the fractional part as well. So that's why we extract the position here instead of marking the dot as the position from where to enter the opening bracket or parentheses. Yes. If we've seen the numerator, we're done. If we've not seen it, we need to make sure that we store in our little hash map the location relative to our current result of that numerator. Then we shift the numerator to the left in decimal notation by multiplying with 10. And then we just perform the same thing as before. We compute the integer division part, and the rest will be the numerator for the next iteration of the loop. Okay, so we're terminating when the numerator is 0 or when we've seen a repeating fraction. And at the very end, we're going to merge all of the strings that we added to our result list. And since we've only added strings everywhere, here, 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 here as well, and here, we won't run into a problem. If we put an integer value in here, join will actually fail. So yeah, I'm kind of confident that this works. Let's just run it, see what happens. Okay, so nice. So the test cases are exactly the examples from the problem description. So they seem to work nicely. And yeah, so next step is to submit it, see what happens. Aha, so I see a problem. So what do we have here? Output is minus minus 1. Oh, I see. I skipped an important step. So actually, after we take care of the sign, we need to make sure that that we remove any negative signs from the numerator and the denominator. So this is mistake. I'm just going to run the tests again. It shouldn't change anything. And now I'm going to submit it. Ta-da! There we go. So that's how that is done. Now let's look at some of the solutions. Let's see what runtime complexity these guys come up with. So first thing is O of n time and space. O of n times space. Why is it O of n times space? Time complexity, O of d. The worst case cycle for all possible remains is 0 to d. Yeah, so to the denominator. Each remainder can appear at most once before the cycle detection. Each iteration is O of 1 operations. So yeah, so O of d. And same for the space. Key inside XOR track. Well, you don't need it. You can just have the two different cases to take care of that. So you don't have to know the XOR. Okay. I don't know why they say O of n when they come up with O of d. So I think we're good with that. And yeah, that concludes this little LeetCode problem.